Hello everyone, welcome to another video in our PySpark interview series. Today we are diving into a crucial topic: what are the key components of PySpark architecture? Whether you're preparing for an interview or just want to better understand how PySpark works under the hood, this video will break down the core components that power PySpark's distributed data processing. From the driver program to executors and the cluster manager, we'll explore each element in detail. Let's get started. Introduction to PySpark. PySpark is the Python interface for Apache Spark, a powerful cluster computing system for large-scale data processing. It allows Python developers to run data processing tasks in parallel across multiple machines, making it ideal for big data workloads. PySpark provides APIs for data manipulation, machine learning, and real-time streaming within a familiar Python environment. Understanding PySpark's architecture is crucial for optimizing applications. It operates by distributing data and tasks across clusters, with Spark's engine handling execution and fault tolerance. By leveraging its distributed computing capabilities, developers can efficiently process massive datasets. Key components of PySpark architecture. 1. Driver program. The driver program is the central component of any PySpark application, acting as the main application that initializes the Spark context and manages the execution of tasks across the cluster. It contains your application's main function, which defines the high-level flow of the program, specifying how data should be processed and what transformations or actions should be applied. The driver program is responsible for converting your user code into Spark jobs, breaking them down into smaller stages that can be distributed for parallel execution. Beyond controlling the workflow, the driver communicates directly with the cluster manager, which is responsible for managing the resources across the cluster. The driver sends tasks to the executor's worker nodes via the cluster manager, coordinating the distribution of data and ensuring that the tasks are executed properly. It also keeps track of task progress and collects the results back from the executors, making the driver program the key orchestrator of the entire Spark application. 2. Spark Session. Spark Session, introduced in Spark 2.0, is the unified entry point for interacting with Spark's various data processing capabilities. It simplifies how users interact with Spark by encapsulating multiple contexts like SparkContext, scope context, and Hypercontext into a single object. Before Spark 2.0, you needed to manage these different contexts separately depending on the task, whether you were working with core Spark, SQL queries, or Hive data. Spark Session brings them all together under one umbrella, making the API more intuitive and easier to use. With Spark Session, you have a consistent interface for performing a wide range of operations, from working with data frames and SQL queries to handling streaming data and machine learning pipelines. Whether you're reading data, transforming it, or writing it to storage, Spark Session acts as the central object through which you interact with Spark's features. This unified approach not only simplifies the development process but also reduces the complexity of managing multiple contexts, making it easier for developers to work with different Spark APIs seamlessly. 3. Cluster Manager. The cluster manager in PySpark is responsible for managing the allocation of resources like CPU and memory across the nodes in a cluster. It ensures tasks are distributed and executed efficiently, allowing for parallel processing of large data sets. By balancing resources and coordinating task execution, the cluster manager plays a key role in optimizing performance and maintaining fault tolerance within the Spark environment. Spark supports several cluster managers. Standalone Spark's built-in cluster manager. Standalone is designed for simplicity and ease of use. It is ideal for smaller clusters or standalone environments where you don't need a complex resource management system. Setting up a standalone cluster is straightforward, making it a good choice for development, testing, or small scale production environments where Spark doesn't need to interact with other systems or share resources. Yarn, yet another resource negotiator, Yarn is commonly used in Hadoop ecosystems where it manages resources for various distributed applications, including Spark. In environments that already use Hadoop, Yarn is often the default choice for resource management. It allows Spark to run alongside Hadoop MapReduce jobs and other applications while efficiently allocating CPU and memory. This makes Yarn a reliable option for large-scale distributed environments where multiple jobs need to share cluster resources. Mesos is a general-purpose cluster manager designed to support multiple distributed applications. It provides fine-grained resource management, allowing different applications like Spark, Kafka, or Hadoop to share resources efficiently. Mesos is well suited for complex environments where diverse distributed systems are running simultaneously, and it offers flexibility in allocating resources based on real time needs, making it ideal for large scale multi tenant environments. Kubernetes is gaining popularity as a cluster manager for Spark, particularly in modern containerized environments. It is an orchestration platform that allows Spark jobs to be deployed, managed, and scaled using containers. Kubernetes offers excellent flexibility, scalability, and fault tolerance, making it a preferred choice for deploying Spark in cloud environments or large containerized infrastructures. It's ideal for organizations that are leveraging containerization for their applications and need a powerful tool for managing resources in those settings. 4. Worker nodes. Worker nodes are the backbone of the Spark cluster responsible for carrying out the actual data processing tasks. These nodes are where the heavy lifting happens as they execute the tasks assigned by the driver program. Each worker node runs one or more executor processes which are responsible for executing the tasks distributed by the driver. Executors perform the transformations and actions on the resilient distributed datasets RDDs or data frames, which are key components of Spark's distributed computing framework. The executors on the worker nodes process data in parallel, allowing Spark to handle large datasets efficiently. They run the operations such as filtering, aggregating, and joining data, and then send the results back to the driver program, which coordinates the overall execution of the Spark job. The worker nodes are crucial because they enable Spark to divide large data processing jobs into smaller tasks and distribute them across multiple nodes, thus enabling parallel processing. This distributed execution model makes Spark incredibly powerful for big data applications where massive datasets need to be processed quickly. The worker nodes play a central role in ensuring that these tasks are executed in parallel across the cluster, maximizing computational resources and speeding up the overall data processing workflow. 5. Executors. Executors are processes that run on the worker nodes in a Spark cluster, and they play a vital role in executing the tasks assigned by the driver program. When a Spark job is initiated, executors are launched on the worker nodes, and their main responsibility is to execute the individual tasks that are part of the broader Spark job. These tasks involve applying transformations and actions to the data, such as filtering, aggregating, or joining RDDs resilient distributed datasets or data frames. In addition to running tasks, executors manage the storage of data. They are responsible for storing intermediate data in memory or on disk, depending on the configuration and the size of the data being processed. This storage is crucial for handling large data sets that may not fit entirely in memory, ensuring that Spark can still process the data efficiently by spilling excess data to disk if necessary. Executors also handle caching, which improves performance by storing frequently used data in memory for quick access across multiple stages of a job. Executors regularly communicate with the driver program, reporting the status of the tasks they are running. They send updates on the progress of tasks, including whether tasks have succeeded, failed, or need to be retried. Once the tasks are completed, executors send the final results back to the driver. This continuous communication ensures that the driver maintains control over the job and can make adjustments as needed, such as rescheduling failed tasks on different nodes, ensuring fault tolerance and reliable execution. 6. Tasks. In PySpark, a task is the smallest unit of work representing a single operation that processes a fraction of the overall dataset. Tasks are created based on the partitions of the data. When a dataset is divided into multiple partitions, Spark creates one task for each partition. These tasks are then distributed across the executors on the worker nodes, allowing Spark to process large datasets in parallel, which is key to its scalability and speed. The driver program is responsible for scheduling tasks. It breaks down the transformations and actions defined by the user into smaller tasks, which are then sent to the executors for execution. Each task handles a specific subset of the data, processing it according to the transformations such as filtering, mapping, or joining applied to the dataset. Since tasks are independent, Spark can run many of them in parallel, distributing them across the available executors and taking full advantage of the cluster's computing power. By processing partitions of data simultaneously, tasks enable PySpark to perform operations quickly and efficiently on large datasets. Once a task completes processing its subset of data, it sends the results back to the executor, which then passes it along to the driver. This parallelism is what allows PySpark to scale easily and handle big data workloads, as multiple tasks can be executed concurrently, significantly reducing the time required to process massive amounts of data. 7. Job and stages. In PySpark, a job is triggered when an action is performed on an RDD or data frame, such as calling collect, save, or count. Actions are the operations that initiate the execution of a series of transformations and cause the results to be returned to the driver or saved to storage. Essentially, a job represents a high level operation that will be executed on a dataset. When an action is invoked, it triggers Spark to begin the actual computation by breaking down the high level operation into smaller tasks that can be executed across the cluster. This process involves executing the various transformations that were applied to the data beforehand. Since transformations in PySpark are lazy, they do not execute until an action is called. At the moment an action is performed, the entire sequence of transformations is executed as a job. Jobs are created whenever an action is called on RDDs or data frames, and they consist of multiple stages depending on the operations that need to be performed on the dataset. These stages are further broken down into tasks which are executed in parallel by the executors on the worker nodes. The result of a job is either returned to the driver program in the case of actions like collect or save to an external storage system, like when using save depending on the specific action that was triggered. Stages. In PySpark, when a job is triggered by an action, it is further divided into smaller units of execution called stages. Each stage represents a collection of tasks that can be executed in parallel on different partitions of the data. The purpose of dividing a job into stages is to optimize the execution of tasks by grouping those that do not depend on each other, allowing Spark to maximize parallelism and efficiency. Stages are determined by shuffle boundaries, which occur when data needs to be rearranged or shuffled between nodes in the cluster. A shuffle typically happens when an operation requires data from different partitions to be exchanged, such as during joins, groupie, or aggregations. When a shuffle is required, it creates a boundary between stages, as the results from the previous stage need to be collected and rearranged before the next stage can start. Within each stage, Spark groups tasks that can be executed without any shuffling of data. These tasks can be processed simultaneously across the available worker nodes, allowing Spark to take full advantage of its distributed architecture. For instance, simple operations like filtering or mapping data can be performed in parallel within a single stage, as they do not require data movement across nodes. A.DAG Directed Acyclic Graph Scheduler. The DAG Directed Acyclic Graph Scheduler is a critical component in PySpark that plays a pivotal role in managing the execution of jobs. When a job is triggered by an action, the DAG scheduler is responsible for breaking the job into stages based on the sequence of transformations and actions defined in the user's code. These stages represent sets of tasks that can be executed independently and in parallel, depending on the data dependencies. A directed acyclic graph DAG is a graph that represents the flow of data and transformations in a Spark application. The term acyclic means that there are no cycles or loops in the graph, ensuring that each transformation is executed in the correct order. The DAG scheduler takes this logical plan, which includes all transformations like map, filter, or groupie, and creates a physical execution plan by dividing the job into stages. These stages are determined by shuffle boundaries points where data needs to be shuffled or rearranged across the cluster. Once the job is divided into stages, the DAG scheduler assigns tasks to executors based on the stages and their dependencies. It ensures that each stage is executed in the correct order, starting with tasks that can be run in parallel and moving on to stages that depend on the output of previous ones. By managing the execution flow in this way, the DAG scheduler optimizes resource usage and ensures that jobs are processed efficiently across the cluster. 9. Catalyst Optimizer. The Catalyst Optimizer is a powerful component in Spark that is specifically designed to optimize the execution of queries in Spark, SQL, and data frames. When you perform operations on data frames or execute SQL queries in PySpark, the Catalyst Optimizer plays a crucial role in improving the efficiency and performance of those operations. It works by analyzing the query or transformations and creating both a logical execution plan and a physical execution plan, which are then optimized before execution. The logical execution plan outlines what operations need to be performed on the data without considering how they will be executed. This includes steps like filtering, joining, and aggregating data. The Catalyst Optimizer improves this plan by applying various optimizations such as predicate pushdown, which reduces the amount of data that needs to be processed by applying filters early in the pipeline. Once the logical plan is optimized, the Catalyst Optimizer generates a physical execution plan which determines how the operations will be executed across the cluster. This includes decisions about how data will be partitioned, shuffled, or cached, and which algorithms will be used for specific operations like joins or aggregations. The optimizer can also choose more efficient execution strategies based on the structure of the data and the available resources, ensuring that the job is executed in the most efficient way possible. 10. Resilient distributed datasets RDDs, data frames, and datasets. In Spark, there are three core abstractions for handling data: resilient distributed datasets RDDs, data frames, and datasets, each offering different levels of functionality and optimization. Resilient distributed datasets RDDs are the foundational data structure in Spark. RDDs represent an immutable, distributed collection of objects that can be processed in parallel across a cluster. The key characteristics of RDDs are their fault tolerance and distributed nature, meaning that if any partition of the data is lost, it can be recomputed from the original data or lineage. RDDs provide fine-grained control over how data is processed, giving users the ability to manage partitioning and transformations manually. However, RDs lack the query optimization features present in higher level IPs like data frames and data sets, which can make working with them less efficient in certain use cases. Data frames are a higher level abstraction compared to RDDs. They are distributed collections of data organized into named columns, similar to tables in relational databases. Data frames provide a more user-friendly API for working with structured and semi-structured data, allowing users to perform SQL-like operations easily. The major advantage of data frames is that they are optimized by Spark's Catalyst Optimizer and Tungsten Execution Engine, which optimize the query execution plan and improve performance by applying various optimizations. This makes data frames a powerful tool for efficiently processing large data sets, while abstracting away much of the complexity involved in managing parallelism and data distribution. Datasets combine the best of both RDDs and data frames. They offer the type safety of RDDs, meaning they enforce compile time checks, which help catch errors before runtime. At the same time, datasets inherit the query optimization features of data frames, benefiting from the Catalyst optimizer for efficient query execution. Datasets provide a middle ground for users who need the type safety and expressiveness of RDDs while also requiring the performance optimizations of data frames. It's important to note that datasets are available only in Scala and Java, not in Python, so PySpark users typically work with data frames instead. And that wraps up our deep dive into the key components of PySpark architecture. We hope this breakdown helped you understand how the different parts of PySpark work together to handle big data efficiently. If you enjoyed this video or found it helpful, make sure to like, subscribe, and hit the bell icon for more PySpark content. Stay tuned for more interview prep tips and tutorials. See you in the next video.